Okay, we're going to go ahead and get started. Good afternoon and welcome to NOAA's National Ocean Service Science Seminar Series. If you are interested in being on NOAA's weekly seminar list, just let me know or Google NOAA Seminar to find out more. And so today is the final seminar in an 8-part climate science seminar series co-hosted by Katie Reeves of the U.S. Global Change Research Program and myself, Tracy Gill from NOAA. I'm going to provide a few logistics about today's seminar and then Katie will introduce the seminar and speaker. We have switched to Adobe Connect for this series to accommodate more participants and to record the seminar. The recording and a PDF of the presentation will be available a few days after the webinar or even a day after, and we will post a link to the recording and the PDF in the chat box. And in fact, I think Katie already has done that. Feel free to ask questions in the chat box and we will try to respond to them as they come, but we may need to wait until the end. People in the room, please sign in and silence your phones. And if you want to make the presentation bigger, there is an icon in the presentation pod that has four arrows pointing to the center or pointing out. That is what toggles your presentation size. And now I'll turn it over to Katie, who will tell us about the upcoming USGCRP pub and introduce our seminar and presenter. Katie?
Great, thank you. Good afternoon, everyone. Thank you for joining us for the 8th and final installment of the Climate Science Special Report webinar series. My name is Katie Reeves, and I'm the Engagement and Communications Lead for the U.S. Global Change Research Program, or USGCRP. I'd like to take a moment to thank NOAA, and in particular Tracy Gill, for making this seminar series happen. We're thrilled to have had the chance to share some of the findings of the Climate Science Special Report with such a large audience, and I hope that these talks were as interesting and helpful to you as they were to me. As I've explained before each of the previous presentations, the Global Change Research Act of 1990 mandates that USGCRP develop a quadrennial national climate assessment. The Climate Science Special Report, which is the focus of this 8-part series, represents Volume 1 of the 4th National Climate Assessment, and it was released in November 2017. The report assesses the physical science of climate change with the focus on the U.S., and it serves as the foundation for Volume 2 of the assessment, which I'll say a bit more about in a moment. You can read and download the Climate Science Special Report at science2017.globalchange.gov, and I'll post a link to the website in the chat box shortly. Before I introduce today's guests, who will wrap up the series by providing a summary of the findings of the Climate Science Special Report, I want to give you a quick update on the 2nd volume of the 4th National Climate Assessment, Impacts, Risks, and Adaptation in the United States. So this report covers climate change-related impacts across 10 regions of the United States and 17 national level topics, including oceans and marine resources, ecosystems and biodiversity, human health, and the built environment. Where possible, it describes local level responses to climate-related risks through the use of case studies. And NCA4 in Volume 2 draws in the expertise of more than 300 authors from around the U.S. and federal agencies, universities, and the public and private sectors. To date, it has undergone 8 rounds of review, including a public comment period and a review by an expert committee of the National Academies of Sciences, Engineering, and Medicine. The assessment is scheduled for release in December of 2018, and we sincerely hope you'll keep an eye out for it. You can find out more about NCA4 Volume 2 at www.globalchange.gov/NCA4. Now, without further ado, I'm pleased to introduce today's talk, the 4th National Climate Assessment and Overview of Volume 1 with Dr. Don Webbles. Dr. Webbles is the Harry E. Preble Professor of Atmospheric Science and a Presidential Fellow at the University of Illinois. He's an expert in atmospheric physics and chemistry with over 500 scientific publications related to the Earth's climate, air quality, and the stratospheric ozone layer. From 2015 to early 2017, Dr. Webbles was Assistant Director with the Office of Science and Technology Policy at the Executive Office of the President. He was head of the Department of Atmospheric Sciences at the University of Illinois for many years, led the development of the School of Earth, Society, and Environment, and was its first director. Dr. Webbles has co-authored a number of scientific assessments, including several international climate assessments led by the Intergovernmental Panel on Climate Change and the 3rd U.S. National Climate Assessment. He's a fellow of the American Association for the Advancement of Science, the American Geophysical Union, and the American Meteorological Society. And of course, Dr. Webbles co-led the Climate Science Special Report, which he will present on today. So thank you, Dr. Webbles, for joining us on today's NOAA Science Seminar. I'll turn it over to you.
Thanks, Katie, and thank you all for attending. It's fantastic having over 100 people coming to listen to me. So as Katie mentioned, I was asked in 2016 to lead the assessment, co-lead the first volume, and then I'm also part of the second volume. But we had our first meeting in April of 2016, and then, as Katie mentioned, we're actually able to publish the assessment in November of last year. I'm going to switch to the next slide. The picture on the front cover on the first slide shows the executive summary is the cover for the executive summary from the report, which is available as a hard copy. And if anybody really wants one, they can either get it through me or through the USGCRP. Otherwise, it is available on the web, and I'll give you the website very shortly. I do want to thank several people that were heavily involved in this. And up front, I want to mention Mike Cooperberg, because Mike played a huge role in not only getting this assessment underway, but also in shepherding it through two different White Houses in the process, and played a huge role in helping us get the final assessment approved. Also, I want to thank the NOAA Climate Program Office for their leadership in the proposal. NOAA was the lead agency, and I want to mention Wayne Higgins for the role that Wayne played in that. And I want to thank all my fellow authors, including my 7 colleagues who gave the previous lectures. Many of the things you're going to hear today are things you've already heard, because they've already gone through a lot of this material in much more detail than I'm going to do today. I'm just going to give you more or less a quick overview. One of the extensive aspects of this is, of the 470 plus page report done by 51 authors, was the role of the Federal Science Steering Committee and kind of overseeing every step of the way. So we had multiple agencies interacting with us through USGCRP and doing this. And this report, much like Katie mentioned for Volume 2, was very extensively reviewed, including a public review, National Academy of Sciences review, and multiple reviews from U.S. agencies, including a final sign-off through the U.S. 13 different U.S. agencies. So it's been very, very extensively reviewed, not only by our colleagues, other scientists, but by the agencies and by the public. So that probably makes it one of the most extensively reviewed reports on climate change ever done. The report itself was intended to be an authoritative assessment of the science of climate change with a focus on the United States. And the reason for doing that was after the third national climate assessment, where we had a kind of one major chapter on the science of climate change and another appendix that I kind of demanded that we have in there to give some further information. People still said, "Oh, there's just not enough on the science." They wanted to hear more about the science, what's known, what's not so well known. Where does the science really stand? And that really became the basis for doing this special volume for the 4th National Climate Assessment. So if you want to see the full assessment, it's available at science2017.globalchange.gov. You can see all 15 chapters plus the executive summary and appendices, etc. Please do that. So what does the assessment tell us? The bottom line is that our climate is changing. It's happening now. It's not sometime in the future. We're really seeing major effects right now. We'll talk a little bit more about that later. It's happening extremely rapidly. In fact, it's happening about 10 times more rapidly than the climate tends to change naturally, at least based on what we've seen as a typical changes in climate since the end of the last ice age. Um, so this is really rapidly, and so it's not surprising that both human and natural systems are having trouble keeping up with those changes. It's not just temperature change. Perhaps much more important, actually, than the temperature change is the changes in severe weather. That severe weather is generally becoming more intense. We'll talk about those specific aspects in a little while. And that sea levels are rising, which have potentially significant impacts, or if actually already having some impacts on coastal areas. It's largely happening because of human activities and the associated pollution, largely the emissions of what are called greenhouse gases, emissions of carbon dioxide and methane, nitrous oxide, and some other gases that are increasing almost entirely because of human activities. We'll talk more about that later. It's not the sun, it's not natural cycles. We'll talk about that. The climate will continue to change over the coming decades, and we'll talk about that also. So I'll move on here. We have many thousands, millions of observations actually that have been made over the last 150 years of the Earth's climate system that tell us a lot about what is going on. So that includes things like air surface temperature and sea surface temperature and temperatures in the upper troposphere, all of which are increasing. And by the way, the temperatures in the stratosphere are decreasing, not only because of the decreases we've had in stratospheric ozone, but also because of the temperature changes there, because of the increases in carbon dioxide and what impacts that has on temperature in the stratosphere. So those things tell us that our understanding of the radiative transfer system are basically correct, that we're capturing what we should be seeing. Ocean heat content is increasing. In fact, 90% of the increase in energy from the increases in those greenhouse gases I mentioned is ending up in the ocean. So if there was more than that, we'd even see larger changes in climate than we're seeing now. But the oceans have been a wonderful reservoir for a lot of that heat. But unfortunately, it means in general the planet is still increasing in temperature, but perhaps not as we're not seeing as rapid an increase on land as we might have seen otherwise. Pacific humidity is increasing. The amount of moisture in the atmosphere is expected to increase because warmer air temperatures should lead to more water vapor in the atmosphere. It's kind of basic physics. That's what is happening. But because of those warmer temperatures, we're also seeing a decrease in snow cover, a decrease in sea ice extent, a decrease in glacial mass balances throughout most of the world, vast majority of the world. So, and there's many other observations. I can't go into all the details here. The temperature overall worldwide has increased about 1.8 degrees Fahrenheit. I'm going to use American units as we did throughout the assessment. In the assessment, we also give metric units as well, because scientists tend to work in metric units. But for the public, American public, we wanted to make sure that we did things in units they're used to. So about 1.8 degrees Fahrenheit, from 1901 to 2016. Now, that may not sound like much, but if you remember that that the last ice age was about 15 degrees Fahrenheit colder than current temperatures, it really says 1.8 is a pretty sizable change. You know, it's like 10% of that. And saying, you know, and you go between what the Earth looks like now and what it was during the last ice age, that's a substantial difference. And it's no wonder we're starting to feel some impacts from this. If you looked at this temperature change on a decadal time scale, you would find that the last 5 decades have seen a pretty significant increase over the previous decade. And it's pretty clear we're going to see that for this decade as well, because 2016 was the warmest year in record, and 2017 was second or third, as we'll talk about shortly. If we take that temperature record, where we have these many thousands of temperature measurements made around the world every day, and then try to go back further by using proxies for temperature, tree rings and coral analyses and borehole analyses on land, etc. There was a whole wide range of these things. And if we put those together, in this case for the Northern Hemisphere where we have the best data, you see that the temperature changes we have now, which is shown in red, which is that those previous observations just put onto this scale, are well above the kind of temperatures that we were seeing over the last 2,000 years. Scientifically, we have the best confidence for the last 1,700 years, but it's pretty clear there really wasn't a whole lot of changes going on before that. Nonetheless, if you looked at that temperature record, that proxy temperature record, you do see the medieval warm period when the Vikings were living in Greenland. And you see the Little Ice Age, the period from the 1600s and 1700s, particularly when it was colder than normal in North America and Europe and much of the Northern Hemisphere. Which, by the way, we think was largely related to really large volcanic eruptions causing that. It was not changes in the sun, even though it was also the period of the Maunder minimum when there was very little sunspots. That doesn't tend to lead to a significant change in the amount of solar flux, though, based on the best analysis today. But the large change of volcanic eruptions cause a cooling effect that can last if they affect the oceans, and in this case, they did. Based on the best evidence we have. So if we look at that temperature record further, instead of averaging over the planet, and let's now look at the planet as a whole, we find that almost all areas of the planet have increased in temperature. You'll see two gray areas there because we didn't have data going back to 1901 for the Arctic or for Antarctica. But nonetheless, as we'll talk about, particularly the Arctic is increasing in temperature more than anywhere else. But overall, if you look at this map, you'll see that the land masses are where the largest increases are occurring. Not surprising, the oceans have a large heat capacity, and therefore they tend to increase at somewhat more slowly. However, there's one really interesting area there where significant decrease in temperature has actually occurred off the coast of Greenland, where the additional fresh water coming into the seawater, into the salty seawater, from the melting ice on Greenland and from melting sea ice has actually had an effect on the circulation in the ocean and is causing a cooling effect in that area, where we're seeing a slowing down of the circulation is helping lead to further ice or further heat being drawn from the surface. So if we go look at that temperature record I had previously, 2016 was the warmest year on record. 2017 actually was either the second or third, depends on which analysis, but very close to 2015 in any case, which was the prior second most warmest year. 2014 was the third warmest year, and then we go back to 2010. So if we go look at the last 18 years since 2000, 17 of those last 18 years have been the warmest year on record. And the exception was 1998, and that was an extremely warm El Nino year. El Nino years tend to be warmer than the average year, and that one was a big El Nino. But clearly, we have seen a significant change over the kind of timescales that we talk about for climate, which is like 30-year timescales. Now, if we go and look at the United States, we've also seen about a 1.8 degree Fahrenheit increase in the U.S. And almost all parts of the U.S. have seen a significant increase in temperature. There are some areas in the southeast where that has not occurred. It's not really clear exactly why that is. It could be due to changes in the weather patterns and such, but It's also thought that maybe that might be related to the deforestation that occurred in the 19th century, followed by the reforestation in the 20th century in the Southeast. But we just don't have enough analysis yet to really fully understand that. We also know that in summer months there tends to be a decrease in temperature in the Midwest, where I live, that a number of analyses have now shown is because of the increase in precipitation, particularly extreme precipitation that we've seen in the Midwest. The soil moisture tends to be higher than it was before, and is kind of helping hold the temperature somewhat cooler in the summer months. If we looked at precipitation patterns, this is where you see that there's been a significant increase in precipitation in some parts of the country, particularly in the Midwest, the Northeast, and throughout the Great Plains, but a decrease in the Southeast and the West. In general, when we look at globally, what we see, and this doesn't exactly hold everywhere, of course, is that the wet are tending to get wetter and the drier are tending to get drier. But it does mean that those very dry areas, such as we have in the Southwest United States, are tending to become even drier and more prone to drought than previously. Now, I've already mentioned the Arctic is changing at twice the rate of the rest of the world, and so they're kind of the canaries in the coal mine for change. Patrick Taylor talked about these changes a few weeks ago, so I'm not going to go into great detail with them, but there's a lot of interesting things going on in the Arctic, including the accelerated melting of sea ice in the summer months particularly, but over year round, we're not seeing as much ice as we did 30 years ago, or anywhere close to it. And a significant loss of mass of land ice from Greenland as well as from most of the major ice masses on the planet. We're also seeing reduced snow cover, and perhaps the most important thing is what's happening to permafrost, because melting permafrost in the Arctic can actually also lead to an increased emission of carbon dioxide and methane that could add further to climate change over the coming decades, and we're still trying to get a handle on just how much that increase could be. Now, I mentioned the importance of seeing of extreme weather. And we are seeing changing trends in extreme weather and climate events, and so I'm going to talk about those. Part of the reason we know that climate change is already really important to the U.S. and to the U.S. economy, as well as to the world economy, is because of what's happening in terms of a growing trend in major climate weather-related disasters, where we have major storms, major events, major heat waves, major droughts, etc., that are affecting the planet. In 1980, NOAA started analyzing such what are called billion-dollar events, and they've accounted for, of course, the change in the cost price index over time. But when you start looking at those early years, typically there was on the order of 2, maybe 3 events per year initially, and now more recent, this last decade, they've now grown to be more like 10, 15, 16 such events per year. And as 2017, which isn't shown in this graph, is I think had 16 or 17 such events. I don't have my notes in front of me, but I think that's what I remember. The total over this time has been about $1.1 trillion increase in cost on the U.S. economy because of these billion-dollar events. This doesn't include any events that cost less than $1 billion. So there's a lot of other smaller events that are also affecting the economy that aren't included here. But we have $1.1 trillion up through 2016, and if we include 2017, it goes up, which was the costliest year in record. it goes up to $1.5 trillion. So people who think that climate change is not affecting them are just wrong. These billion-dollar events have happened in all parts of the country, and the cost on the American consumer and taxpayer has been quite extensive. We just don't tend to count that when we're thinking about the changes that are occurring. In 2018, we've already seen over 6 events. This is up just through June. I think there's been a number of wildfires in the West that have probably been billion-dollar events since then. So I'm sure it's much higher already. And we've seen major headlines throughout not only the US, but throughout the world. And in fact, it's got to the point where scientists like myself are wondering, are our models under-predicting the changes that are occurring? Are they occurring so much, or the severe weather type events occurring so much more extensively with more intensity than that our models even tell us they should have been? Is there something wrong that we need to better understand? And so I've actually been discussing with some scientists the question of whether we ought to have a special meeting to just kind of discuss, what's going on. Do we need further improvements in our modeling capabilities in order to understand what is going on with severe weather? It's actually quite frightening when you look at what all the events that have happened this year around the world. It's kind of amazing. Well, overall, looking globally and at the United States, heat waves are increasing, number of heat waves, and the intensity of heat waves. That's particularly true in the US since about 1970, 1960s. In the US, the largest heat waves were still those that occurred in the 1930s, but they were an anomaly compared to what was going on globally. So if you looked at globally, the amount of heat waves have generally increased since 1900, when we first started having enough data. Cold waves generally are decreasing. That doesn't mean we don't get an occasional cold wave. We do expect that, and we had some here in the Midwest actually this last winter. But overall, they're decreasing. When it rains or snows, it's more likely to be a larger event. Analyses are very clearly showing this increasing tendency by decade over the last four decades. And the projections are that will continue. So when you get rain or snow, more precipitation is likely to come as a larger event. That's leading in some areas where you're getting particularly significant number of these events, such as the Northeast and Midwest, for more likelihood of a risk of flooding, like we just had in Pennsylvania quite recently. But it's also really because of how the rainfall is being distributed, we're getting an increasing tendency for intense droughts, particularly in the Southwest and the Southeast. Wildfires, as a result of both increasing temperature and less rainfall, have led to significantly large wildfires in the West and Alaska. It's not that the number of wildfires is increasing, but the number of intense wildfires is increasing. We're likewise seeing some evidence of increasing intensity of Atlantic hurricanes, and certainly the best analyses we have using very high resolution models, as well as theory, tell us that hurricanes are likely to be more intense in the future. Not greater in number necessarily, but more increasing intensity. Tornado activity, the jury is still out. We've seen an increase in outbreaks, but the scientific evidence could go and suggest that that tornado activity could go in either direction, towards either becoming more intense or less intense in the future, depending on several different factors. So it's something we're still trying to understand. Paper that was just published today by one of my students was one of the first analyses of hail across the nation, And her analyses and her thesis, we're still publishing a paper relating to this, suggests that hail is becoming more intense with the changes in climate. And that's a big concern because hail causes a lot of damage across the country. All of these trends are likely to continue into the coming decades. Extreme heat events are increasing in most regions of the world, including the United States, and one of the ways we know that is through record highs versus record lows. There's many more record highs happening relative to record lows. As already mentioned, the amount of precipitation is increasing over time. Graph on the left is the 2-day precipitation events exceeding 5-year reoccurrence, so 1 in 5-year type events, and showing a significant increase since 1970. And to put that another way, the top 1% of the events since 1958 have increased by 42% in the Midwest and 55% in the Northeast, and has increased throughout almost the entire nation. The only places that isn't readily seen is over the islands like Hawaii and Puerto Rico, where they're so dependent on major storms in terms of the total rainfall that if there's a downturn, as there was in recent years, they're not seeing it. But previous analysis showed that the islands kind of jump all over the place. Sometimes the long-term trend is increasing, sometimes it's decreasing, and it's all because of that change in intensity. But otherwise, the main continental parts of the United States are all seeing an increase in precipitation coming as larger events. So even though there's an overall decrease in precipitation in the Southwest, for example, when it does rain, it is likely to be a larger event than it was previously. This is from a new analysis that's in press. Since I'm giving the talk, this is actually a new study, not just something that came out of the assessment, but it further amplifies something that was seen in the assessment that I don't have time to go through this in detail, but basically we're tending that the tendency for the coming decades is that we'll have less days, and this is for the continental United States and for various parts of the continental United States. The paper is in press. It's been accepted. But basically it shows that when likely to have more days throughout much of the country when you have no precipitation, more days with very little precipitation, and more days with, so less days, with little precipitation, and more days with greater precipitation. So the most extreme, the top 1% events or so, or the top 5-10% events are likely to increase quite dramatically. This just follows in line with the analysis we've been seeing for the past and the projections made in the future, but this is a very fine resolution regional modeling study to look at that. I've already mentioned the increase in wildfires. We had over 9.2 million U.S. acres burned in 2017. Similar amount is happening in 2018. I don't have the exact numbers. Last I knew it was around 6.6 or so, but that's from a month ago. So it's probably an underestimate of what it is now. The fire season tending to last longer because of the changes in temperature. The average fire tends to be much bigger and hotter than before, sometimes hundreds of degrees hotter. And in Alaska, even the tundra is experiencing wildfire. So in the West and in Alaska, we're particularly seeing a more significant amount of wildfires. I've already mentioned that the tendency for more intense hurricanes. There's more ocean energy from the increase in temperature in the oceans and leading to potentially stronger cyclones, with more precipitation. But the analysis don't suggest an overall increase in the number of storms. And of course, as sea level is rising, which is also occurring, the frequency and intensity of extreme flooding associated with coastal storms is also tending to increase. There are many different studies examining detection and attribution. I know you had a nice presentation from Tom Knudsen about that. That was one of our chapters in the report, was on detection and attribution. Many, many analyses are going on daily now, looking at specific events as they happen to understand what role did climate change play in those events. And for example, for Hurricane Harvey, the occurrence is 3 to 3.5 times more likely, and it's based on 3 different published studies now, and rainfall 15 to 38% greater. Basically, what is a 1% chance per year now is by the end of the century could become an 18 chance each year of having an event like Hurricane Harvey. So much more likely as we got over time. Now, what is causing all these observed changes? I've already mentioned the importance of the greenhouse gases. It's not the sun. The sun, if anything, has decreased slightly in terms of output, not increase. There are no natural cycles in the observational record that can explain the observed changes in climate. This led to a conclusion in the assessment that there are no credible alternative explanations supported by the extent of the observational evidence, that the changes we're seeing can largely be explained by the changes in the greenhouse gas emissions that have happened, the concentrations, and what that means to the radiative transfer system in the Earth's atmosphere, and how that affects our climate. Well, if we looked at the current amount of carbon dioxide in the atmosphere, we're currently sitting at about 405 parts per million. I haven't checked it in recent days, but it's right around 405 parts per million. It's a very small amount of CO2, but CO2 plays a very important role because of the absorption it has in the infrared wavelengths. And if you compare that concentration with past concentrations using ice core analyses, we can go back 800,000 years and see that the current concentrations are well above anything we had seen in between previous ice ages or during ice ages. Ice ages tend to be about 180 to 200 parts per million. In between ice ages, they tend to be about 280 to 300 parts per million. And now we're sitting at 405. So we've seen a very significant increase in concentration. And the last time we saw such concentrations was about 3 million years ago, when the Earth was much, much warmer than it is now, as a result of having been at those kind of concentrations for many, many thousands, or several thousands of years. So, and which we think was largely related to outgassing from volcanoes, and during that time period, that's not happening now. Well, if we try to say, well, what other analysis have we done to try to understand this attribution of climate change to human activities? We can look at the forcing on climate. Since humans really began to extensively modify the concentrations of these greenhouse gases, which started basically with the Industrial Revolution. So if we go back to 1750, we see that the human forcing on climate from this increase in greenhouse gases has been by far the most significant. Very, very minor effects from the changes in sun over that time period, the fluctuations in the solar output over that time period, and the volcanic eruptions would largely have caused a cooling due to the sulfur put into the atmosphere, which causes a cooling effect. We could likewise compare the observed temperature record, like I showed you in one of the first slides, with what we get, first of all, in the right-hand side. If we only included natural forcings on the climate system, we cannot explain the changes in temperature we've seen over the last 40 years. You can explain a lot of what was going on before that, but going back to about 1970, you really can't explain what has happened. But if you include the effects of the greenhouse gases, you do a much better overall job of understanding what has happened to the temperature record. And then in this case, it compares the three. In the first slide I just showed, earlier slide, I showed you the NOAA observed data set, but there are multiple other analyses of such things, all of which agree quite closely to each other. So what's included here is also the NASA GISS and the UK Hadley Center analyses as well. Now, we expect these projections of climate to continue to change into the future based on the emissions that humans are making now of CO2 and methane, et cetera, and what that means in terms of future concentrations of those gases, leading overall, if we continue the pathway we're on now, which is kind of the highest pathway here, heavily using fossil fuels, then we could end up as high as 8, 9, 10 degree temperature change by the end of the century. Hopefully we won't be following that pathway. We'll choose something quite a bit lower. The other case we tended to look at in this assessment was RCP 4.5, which assumes you start transitioning away from the use of fossil fuels to alternative energy and transportation, such that you reduce emissions greatly over the century and reduce the overall effects that you're seeing more like a 3 to 5 Fahrenheit increase in temperature. And we looked at one further case, which was also looked at in one of the more detailed, chapter 14 in one of the presentations, where we looked at a case where requiring action be taken, significant action, in order to try to keep the temperature down below 2 degrees centigrade, 3.8 degrees Fahrenheit, and that's called RCP 2.6. I'm mostly going to talk about the differences between the high case and the lower 4.5 case in the rest of the presentation. If you looked out over the coming decades, the next few decades, there's very little difference between any of the scenarios because the emissions we've already made are going to have their most significant effect over that time. You do see, another 1.5 or Fahrenheit, or this, I'm sorry, this is in degrees centigrade. I didn't show the one in Fahrenheit here. Over the next few decades, compared to 1986 to 2015. But if by mid-century you start seeing a significant difference in the scenarios, and by the end of the century there's a very large significance with the significant difference with the largest effects on land, as we had talked about earlier about the changes we've already seen, and the highest changes occurring in the Arctic, where the melting of ice is leading to significant feedbacks on the Earth's climate system. If we looked at the mid-century and late century for the high scenario, which is on the right here, and the lower scenario, the RCP 4.5 on the left here, we see very significant differences already at mid-century, but particularly by the end of the century. And by the end of the century, with the high case, we're talking 8, 10, 12 degree Fahrenheit increases in temperature over major parts of the U.S., whereas in the lower case, we're talking more like 4 to 6 degree changes. Precipitation, again, the wet tend to get wetter and the dry tend to get drier, particularly a heavy drying out of the southwest is expected. And the Midwest and Northeast are likely to, and most of Alaska are likely to see a significant increase in precipitation, with much of that precipitation again coming as larger events as compared to the past. If we looked at the number of days above 90 degrees Fahrenheit, this is for the continental U.S., by mid-century we're talking about, and this is the high emissions case, but not a huge difference between the low emissions and the high emissions case here. We could see as much as another 1 to 2 months increase in 90 degrees days or above. So significantly more heating, much longer summer season in a sense. And but if we also look at the days below freezing, almost all parts of the U.S. are going to see a significant decrease in the number of days below freezing, again by another 1 to 2 months. by mid-century. Increases in precipitation coming as larger events. This is from another study that I think is in the assessment that looks at 2-day, 5-year return type events over various parts of the country. Seem to have lost slides here. What happened to 31? So I'm not seeing slides. Tracy, do you know what's going on?
You're not seeing any slides?
No, the slides just went away.
Oh. Okay, so Don, we can see your, yeah.
You can see them?
Yep.
Yep, I can see your widespread ocean impacts.
Did the whole framework disappear, Don?
Yeah, I just have, it says slide 31 and there's nothing on it.
Oh, is this the changing ocean slide?
Yeah, it probably is. If you guys can see, if everybody can see it, okay, I'll just keep going on because I know what's on the slides.
Sure.
I'm almost at the end anyway. But basically, you just had a talk by Billy Sweet talking about what's going on in the oceans. We've seen a sea level rise of about 7 to 8 inches since 1900. That's already having a significant impact on causing nuisance flooding and in some major parts of the United States, and having an impact worldwide. Over this century, we should see about another 1 to 4 feet of increased sea level rise. But in our analysis, we couldn't say that this wouldn't be as that this could be as large as 8 feet, and that's because of the uncertainty about what's happening in West Antarctica, where there's a significant concern about basically getting rid of the column of ice into the ocean there that would then basically allow the ice off the mountains in West Antarctica to just basically slide into the ocean. If that were to occur, then 8 feet is possible, and that would have a very significant effect, of course, on the coastlines in the United States and elsewhere. We have seen an acceleration in sea level rise, and the highest rate now, I mean, the rate of increase now is the highest it's been in at least 2,800 years. And that's led to an acidification of the oceans, the increase in CO2, about 25% of that CO2 is ending up in the oceans. Part of it ends up in the biosphere, part of it ends up in the oceans. And that's in the oceans, that CO2 turns into carbonic acid, which tends to acidify the oceans, basically making them less basic. And so that is a concern to shellfish. And so there's a lot of concerns about that. Something we're still trying to fully get our handle on, trying to understand better, but potentially very significant to wildlife in the oceans over this century. And we're seeing these changes. Yes.
Can you tell me which slide you're on, and I'll make sure we're on the slide that you're on.
I'm still on 31.
35?
31.
31. Okay, I'm sorry. Thank you.
You should say the changing ocean.
Is that 31?
Perfect. Yep. You'll go back, Tracy, to the one with the picture on it.
Oh, is this 31? I can't see it.
That's it. Yep.
Yeah.
Now we're up to 37.
Yeah.
36, 35, 34.
See, all mine are blank, so I can't see anything. So can you page it from there?
We're on 32, where the coral reef page.
Coral
Okay, and where do you want to be, Don?
32. I'm sorry, 32 is, yeah, mine went blank after 31. So 32 is where I want to be, but I've just did that one. So let's do 33.
Okay.
So that just shows the increase in nuisance flooding, tidal flooding that has happened in Norfolk, Virginia when there's a high tide. We're tending to get streets flooded, and it's getting worse and worse of a problem year by year. So that is becoming a real issue throughout much of the United States, much of the East Coast and the Southeast, and even in California as well. And the next slide is 34, which shows that is projected to even further increase over the coming decades. So street flooding is becoming a way of life in certain parts of our cities and our coastal cities, and potentially coming into such a big problem that's probably some lower lands or just lower parts of the cities are just going to have to be left uninhabited. Go to 35, that just shows the sea level rise. I've already explained everything on there, basically, another 1 to 4 feet by the end of the century. And 36 shows that certain parts of the U.S., particularly the east and the southeast, the land is also subsiding. And so given that, plus the effects of wave actions on perceived sea level rise in any given area, means that much of that area is going to, if there was a 3 feet or 3.3 feet, 1 meter increase in sea level rise by the end of the century, we have areas in the east and southeast that may see 4, 5, 6 feet of sea level rise. So much higher than the global average. That's a very significant change. And so if I go to the last slide, 37, and unfortunately I just cannot page anything on my computer.
0 to 37.
Okay, good. The that has to do with chapter 15, where we looked at potential surprises. Are there things that we just don't know well enough that could make climate change either less likely or more likely to be impactful upon the American people? What we found was that there were very few cases of indicating likely to be less impactful. And so the chapter mostly concentrates on those things that could be even more impactful, those things that are called tipping points, for example, such as the changes in permafrost I mentioned earlier and how that could further add to the overall climate change if we get significant emissions of carbon dioxide and methane. The changes in the Arctic in general, many of those can have some significant impacts. And there was others, but so there was a couple of things we talk about in that chapter. One is the aspect of tipping points and significant changes and that those could have on the Earth's climate system. But the other thing we talked about is having multiple severe events happen simultaneously, having a severe drought with a large heat wave, and that those kind of events have not really been taken into account in past analysis of impacts, and we really need to consider those in the future, that multiple events could become much more common. And so I'm going to leave it there. I didn't put a real summary slide into this talk, as I usually do, but I also figured I'd be running out of time. So thank you all, and I'd be happy to answer any questions you might have.
Great, thank you, Don. We had several questions. Let me see if I can scroll back up. Can you even see the question chat box, Don?
I can.
You can?
I can. No, that is fine. It's just the slides went away.
So he said he could hear him, right?
Yeah.
Okay. So if you want to look at some of the questions, I'm scrolling down to the first one. Will NOAA do a similar series? Oh, no, that's for the seminar series. I'm looking for a question relative to your talk. There are several. Hold on. people said they were excellent webinars, which is great. And
They're
coming down to
Tracy, I've got it. I've got it.
Go ahead,
from
Katie.
Tracy, I can read it. Yep.
Okay.
So, question from Dave Helms, and that is, who is working on econ data cause-effect relationship? Not enough to state that we are seeing expensive events.
Yeah. So what people have been doing is various scientists, and Tom Knudsen I think, talked about some of this in his presentation. But what has happened since the assessment was done even is that scientists are almost taking events real time now and trying to say, well, what role did climate play in that event? That's been going on with a lot of what's going on in Europe and in the Asia this year, for example. And the economic analyses, I'm not sure, but we're using the severity of looking at very severe events and then trying to look at the science. And that is being done by a large number of scientists throughout the world that are trying to, as I said, almost do this real time now.
Okay. And I'm going to skip over Dave's second question just to tackle another econ-related question from Nicole Metzger, and that is, has anyone assessed the damage values to total value in the areas affected? If climate factors remain the same, there would still be an increase in damages per event simply due to the development increases, especially in risk-prone areas. It would be interesting to see that difference.
Oh, I agree, and I was very concerned about that because one of the aspects was when the NOAA analysis started becoming available and I started showing them at meetings, people would say, well, isn't a lot of that just due to people having moved the coastlines and they're getting hit by hurricanes and the population has increased? It's certainly a factor, and so I asked NOAA to do an analysis of just removing all the hurricanes, and you still saw the same tendency overall. And it's still essentially the same kind of rate of increase. And if you went globally again, you saw the same thing. And so so it isn't just population. Certainly, the population movement has had some impact on looking at that, but it's not just that. It's the fact that we're actually seeing these events everywhere. That tells us that it's more than just population.
Thanks. Another from Dave Helms, and that is, how is hail intensity measured?
So the student who did this analysis used radar data to look at both the size and the length of a hailstorm to help determine that. But a lot of that was based on the size of the
and
hail.
Katie, many of the questions that Dave Helm has, I think they probably are answered in volume 1, aren't they?
Well, yeah, some of them are, and I will share another link, but I just wanted to...
Largely, but yeah. So the hail thing is mostly new. As I said, that's just based on a newly published paper. Okay. So that's which is the first one. We do discuss hail in the assessment, but we mostly said that we just didn't have enough data at that point. But since then, we've had these new analyses suggesting that.
Okay, great.
Much like
and then
in general,
I'm going to
or precipitation in general, hail is also becoming more intense.
Excellent. Thanks, Don. And then Dave, regarding your carbon question, I have a link to an infographic that was shared by our executive director that I can drop into the chat momentarily. Okay. So let's see. Barb was asking if we have similar slides or graphics, including Alaska and Hawaii, and I think that's a reference to one of the sea level rise graphics on a previous slide. Unfortunately, I don't have that in front of me.
The Patrick Taylor in his presentation did talk a lot about the findings that we had on the Arctic and Alaska. things like sea level rise are not as much of a concern in Alaska because the land is actually uprising as partially as a result of the ice rebound effects. As the ice is melting, the land is increasing in Greenland and parts of the Arctic. But there are still significant problems because as the sea ice is melting, we're getting significant wave actions in northern parts of Alaska that are still leading to coastal erosion, significant coastal erosion, such that some villages like Shishmaref are basically having to move the location of the village to avoid the fact that the wave effects are going to basically wipe out their village.
Okay, great. I'm seeing a lot of questions in here about specific mitigation policies and things, and I want to just stress that the National Climate Assessment in both ends is really a policy relevant but not policy prescriptive document. So there's not a lot of specific work on policy recommendations. Don, is there anything else you'd like to say about that?
Well, I mean, there's the obvious things. For one, there's a lot we need to be doing in terms of mitigating and adapting, because we will not be able to totally slow down climate change no matter which pathway we were to actually follow. And so we are going to have to adapt. Hopefully we can stay away from the largest changes and keep to the smaller ones. Basically we have three choices. We can mitigate, we can adapt, or we can suffer. And right now we're kind of doing all three. And as we go forward, hopefully we'll do enough mitigation to avoid the worst of the changes and enough adaptation to work well for society. But we are going to have to do those things.
Great.
And
then I think just one more question.
Easy thing for mitigation, by the way, is sorry. Go ahead.
Go ahead, Don.
I was just going to say that energy efficiency is a big thing all of us can be working on in our own homes. And if I were to emphasize anything to everybody, is to let their political representatives know that climate change is a very important issue to us now and to our futures, and something we should all be trying to do something about.
Great. And then one final question, I think, Don, if you have a minute, and that is from Tim Mock, and he's asking, what's causing the recent, in the last few years, acceleration of global warming, illustrated by the GHG radiative forcing data?
I don't know what he means by the. Was that greenhouse gas forcing data?
Yeah.
Okay. Well, we don't measure radiative forcing directly globally, but overall it's increasing. We've seen an acceleration in the amount of CO2 increase. We had a slowdown during the economic due to economic changes in the 2009-2010 time period. But in recent years, we've seen an acceleration again in the amount of CO2 increase. I'm hoping that's going to be short-lived, as people around the world are now thinking heavily about trying to switch to alternative energy. Just this year, recent analyses have suggested that solar has become even cheaper than natural gas. So the cheapest form of energy actually may be solar. And so if we can adapt to that quickly, we can avoid a lot of those emissions we're currently making. But there's a number of reasons why that occurred. But but the increase in emissions, recently seems to be largely related to economic factors.
Okay,
All right.
great. I think that's it. If I might just say real quickly, thank you, Don, so much. Thank you, Tracy. Please, everyone, keep an eye out this later this year for volume 2 of this assessment, as well as the second state of the carbon cycle report, which should be released later this year. That really takes a look at the carbon cycle for North America.
Katie, can I answer one more question
yeah.
real quick? I saw that there was one about sea level rise.
Okay.
Thermal expansion is largely explained what we saw in the past, but the ice melting from land ice is probably the more important to the future. And so what's happening in Greenland with glaciers and what's in Antarctica, I think, are going to largely control sea level rise over this century.
Great. Thanks, Don.
Okay. Well, thanks, everybody. Any last words? Katie, you're done?
Well, thank you all for attending. I really appreciate it. If you have any personal questions for me, want to know more, just send me an email. I'll be happy to address them.
Okay, and Don, do you mind if I drop your email into the chat box?
No, it's fine.
Okay, I'll do that.
Webbles@illinois.edu.
All right, folks, thanks for joining us. And Katie, thanks for putting this together. It was great. And for who was the person that helped you pull all the names together? I forgot who you said that was.
That's Dave Dockin. Dave Dockin is a superhero around here. He does a lot of work, and he helped shepherd the CSSR to completion. So he has been tremendously helpful.
Great.
You have a lot of superheroes around USGCRP, including yourself, Katie. Dave is certainly another one. Great help to me. Dave was my right hand in terms of getting this assessment completed, because he would, I would ask people to do certain things. Dave would keep on them to make sure they were done. Great help. And as I mentioned earlier, Mike Cooperberg was also a big help.
All right, thanks for joining us, everyone, and hopefully we'll have another webinar series next year to bring you volume 2. Bye-bye.
Great. Thanks so much, everyone. Take care.